So this is topic 6.3, heat transfer and thermal equilibrium. So the main learning objective today is to explain the relationship between the transfer of thermal energy and molecular collisions. So this is continuing, we're going to continue talking about heat transfer, heat exchange, a warmer body versus a cooler body, and we're going to introduce a concept called thermal equilibrium. So back in Unit 3.5, we talked about the Maxwell-Boltzmann distribution curves and how different temperatures, if they have a substance at different temperatures, what is happening to the kinetic energy or what is happening to the velocity of molecules and all that type of stuff. Remember that kinetic energy is half mass times velocity squared. And when we talk about temperature, we're actually looking at the average kinetic energy of all the particles that are found there. If you have a higher temperature, you're going to have a higher kinetic energy. When you have hotter particles and colder particles interact with each other, they collide, energy is transferred between them. So this is what we're talking about with heat transfer, heat exchange, and this results in the hotter particles losing some of their energy and the colder substance is increasing in temperature. So when we're talking about heat, how it's transferred, it goes from the hotter to the colder substance. If the two substances result in the same temp, we call that thermal equilibrium. So that's an important thing you need to be mindful of. Thermal equilibrium. When the two substances reach the same temperature, they now have the same kinetic energy. So you have 50 grams of aluminum with a specific heat of 0.9 joules per gram degree Celsius at 85 degrees. It was placed into 100 grams of water, and that has its own specific heat and all that. What happens at 25 degrees Celsius? So what is happening to the temperature, average kinetic energy, and the average speed of the aluminum? So think about which way heat is traveling. So your piece of aluminum is hotter than the water that it's being put into. So heat is going to transfer from the aluminum to the water, eventually raising the temperature a little bit of the water. But what's happening is that you notice that the aluminum is being placed in a much colder surrounding, so to speak. So what is happening at a temperature, the average kinetic energy, and the average speed of the aluminum. So essentially, if you know that temperature is decreasing, so temperature is decreasing, so is the kinetic energy, and therefore the average speed as well is also going, this average speed is also decreasing. Get rid of that. So essentially everything is decreasing. So the 50 grams of aluminum is placed into 100 grams of water at 25 degrees. The aluminum is 85 degrees Celsius. The final temperature you end up finding is the two substances, they have the same temperature of 30.8 degrees Celsius. So what can be said of the temperature changes for each substance? So when we're looking at this, we can see that the initial temperature of the aluminum is 85 degrees Celsius, and the final temperature is 30.8 degrees Celsius. The initial temperature of the water is 25 degrees Celsius, and the final temperature is 30.8 degrees Celsius. So the final thing to kind of take away from this, like with all this information, the temperature change, so delta T of aluminum is greater than the temperature change of the water. What is true of the thermal energy exchanged? So as you know, as you're decreasing the temperature, decreasing the temperature of the aluminum, you're also increasing the temperature of the water at the same time. So notice how they have different specific heat capacities. So in the end, if and when you reach thermal equilibrium at the same temperature, like we said, so the sorry. So in the end, the amount of thermal energy exchanged for both of these substances will be the same magnitude, so the same number, if you will, of thermal energy, but they, oops, but in opposite directions. So that's it for now. Please work on your 6.3 practice problems. Thank you.